Okay, so this is actually chapter 4, unit 3, chapter 4. We're talking about the atomic structure. This is the unit that actually has a lot of history. I focused on the history in this unit a little bit more because it's very important, because it's not just, we all know what an atom's made out of. You should already know that, but I'm trying to teach you how we got to that point. Okay, so let's start off with Democritus. This was a long time ago. Look at the date. This was 460 to 370 BC. So a long time ago. He was the first person to suggest the existence of atoms. So he actually gave them a word, and he was Greek, so he spoke in Greek. He called it atomos. We shortened it to atoms. But he was the first one to actually state what he thought an atom was. So he said that atoms are indivisible and indestructible. What does indivisible mean? You can't divide it up. What does indestructible mean? You can't destroy it. Okay. His ideas did agree with later scientific theory, but they did not explain how chemical behavior works. They didn't explain why things react sometimes and why they don't other times. He didn't understand why we get compounds the way we do, so on and so forth. Plus, can atoms be divided up further? Yes. Atoms can be divided up further, but we didn't know this at that time frame, right? Okay, Democritus was also a philosopher, which means that his method was not based on the scientific method. He did not do experiments. So he said, oh, atoms are indivisible and indestructible, but he just left it at that. He never tried to test it. He never tried to test to see if he could divide up an atom more. He was a philosopher, not a scientist. Okay, so let's look at the years again. Democritus, we're looking at 370 BC, correct? Okay, the next scientist we're going to talk about was 1766. What do you think? Isn't that a giant gap? Why do you think there's such a big gap between 370 BC and 1766? Why was there such a gap before the next person tried to decide what an atom was? Did we have any way to test it? No. Nobody had a way to test it. Nobody had a way to do an experiment on it, so we just went with what he said because nobody could prove him wrong or right. Okay? So then came John Dalton in the late 1700s. He has a 4-part theory, which is a short answer question on your test, not a multiple choice, short answer. I ask you to state the 4 parts of his theory. The first part says all elements are composed of tiny, indivisible particles called atoms. So basically he agreed with Democritus. He said atoms cannot be divided. They are as small as you can get. The second part of his theory said atoms of the same element are identical. So every single oxygen atom is going to be identical to every other oxygen atom. Oxygen is oxygen is oxygen. Okay, he also said that oxygen, it will be completely different from a different element, like fluorine. They will have nothing in common. Oxygen is oxygen, fluorine is fluorine, they have nothing in common. The third part of his theory said atoms of different elements combine in simple whole number ratios to form chemical compounds. For some reason, this is the one that's always hard for us to remember and for us to explain. But basically what this means is, if we take a compound such as salt, we all know that salt is made out of sodium and chlorine, right? So when we combine it, we're going to combine it with 1 sodium and 1 chlorine. We're not going to combine it with half a sodium atom and half a chlorine atom. They have to combine in whole numbers. And then the fourth part of his theory says, in chemical reaction, atoms are combined, separated, or rearranged, but they are never changed into atoms of another element. Another way to think of his fourth part of his theory is conservation of mass. We can't lose oxygen. If we start with 4 atoms of oxygen, we have to end with 4 atoms of oxygen. They may not be in the same form. They may be bonded to a different element, but if we start with 4 oxygens, we have to end with 4 oxygens. Now, do you think his theory is true now? Do we hold his theory to be 100% true right now? No, but again, this is as best we could do at the time frame, right? So, just to kind of give you guys a visual of how small an atom is, can we see atoms? No. Okay, so let's try to give you a small visual example. Okay, so elements are able to be subdivided. They can be subdivided into smaller and smaller and smaller atoms, but let me ask you a question. We can break up an atom, correct? So if I take oxygen and I break it up farther, we can break atoms down into smaller particles. Is it still oxygen? No. If I take an oxygen atom and I break it down into smaller pieces, it's not oxygen anymore. So elements are technically as small as you can get before you start losing properties. So, how small is an atom? If I took 100 million copper atoms, so think about how big 100 million is. That's a lot. If I took 100 million atoms of copper, I would only have a line 1 centimeter long. Now, could I see this line? No, because it may be 1 centimeter long, but it's still really, 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 really skinny because atoms are really small in all directions, correct? So in order for me to get something I could actually see, I would probably need at least a 1 centimeter cube, right? So if we have a 1 centimeter cube of copper, it's going to be 100 million by 100 million by 100 million, right? So that would be a 1 with 18 zeros after it. That's how many atoms of copper I would need to make a 1 centimeter cube of copper. That's a lot, correct? So copper is used in your house and your plumbing a lot. So think about how many atoms you must have in your house just in your copper line. Okay, can we see atoms? No. We actually don't have an instrument that actually allows us to see atoms. However, we can observe them. We can't see them, but we can observe them, and then the computer can give us images. We can't ever see them though. So we actually use an instrument called a scanning tunneling microscope, and I like to compare this to those old music boxes. Girls, I'm sure you've seen them. Boys, I'm not sure. But have you guys ever seen the music boxes that have it almost looks like a piece of a round thread thing, and it turns, and it's metal, and it has the bumps on it, and then it goes and it moves. It has this like metal pieces that it moves, and when the metal pieces move, it produces sound. Okay, that's what the scanning tunneling microscope's kind of like. It scans across the surface, and as it reaches an atom, it makes these metal things go up. And as they fall back down, we are allowed to see not only was an atom there, but we can also guesstimate how big the atom is. Okay, so every single time it comes up to an atom, it moves just a slightest bit. Okay, so let's keep going in the history of the atom. The next scientist that we are going to talk about is Dalton. Okay, first, we already talked about the fact that his first part of his theory was incorrect, right? We know that atoms are divisible. We know we can break them up. What can we break them down into? What are they called? 3 things. Electrons, protons, and neutrons. These are called subatomic particles. So on your test, when I ask a question about subatomic particles, I'm not asking you a hard question. I'm asking you about protons, neutrons, and electrons, okay? Now, are there more subatomic particles than those 3? Yes. There are ones such as quarks, but we're not really going to talk about them this year. Okay, we're going to focus on these 3 and how they act. Okay, so we found Dalton's first part of his theory to be incorrect because now we know about protons, neutrons, and electrons. But how did we come across this? How did we figure all of this out? Well, the first scientist to start to figure out or study these 3 things was J.J. Thomson, and he did an experiment with something called a cathode ray tube. Do you remember this from the video yesterday? Okay, so if we look at the picture, in here in the center, we have P2 that has some sort of element in it, correct? As the element comes out, we then apply a charge to it. We apply electricity to it, right? So it's kind of like a battery. Here we have our battery. We have it going to two separate ends. One end is negatively charged. One end is positively charged. Looks similar to a battery, right? As we apply electricity to it, the element gets, what I like to say, excited. I know that sounds silly. But it gets excited in the process. It starts to emit light, which is why in the movie yesterday you could see the green in the tube. Okay? But as we notice, here we can see our green, right here in the center. But as we notice, as we bring a negative plate up to it, our green starts to move up, right? And then also it starts to go over our anode and it starts to be attracted to the plus side. So if it's going away from the negative but towards the positive, what is that telling us? It is probably negatively charged, correct? Okay, so can anybody think of an example of how we could use this in our classroom right now? There's one in this room right now. Okay, this is a cathode ray tube. These old TVs, or the old monitors that have the box in the back, not your computer monitor screen, probably not your nice TVs at your house, or maybe in the basement at your house and you have the old TV, or maybe in the garage, okay? These have a cathode ray tube, which is why when you turn them on, you hear that noise. Don't you hear that kind of like buzzing sound? And then doesn't it take the picture a second to get there? So let's watch. So I push the power button, and we're waiting, and we're waiting, and we're waiting. Oh, and finally the picture starts to pop up, right? Okay, why do you think it's taking so long, the delay? Why is it taking so long for the picture to come up? Because it needs time to make the element excited, right? And then we have to wait for the electrons to move to where they're supposed to go, right? For us to be able to see the picture. Now also, if I turn the power off, watch what happens to the picture. What did you notice? What did it do? It shrunk into a line in the center of the screen, correct? If you look at the picture of our cathode ray tube, what do you notice right here? There's a slit in where the element is coming out, right? So that is why in the TV it goes to that slit first, because that's where the stuff is originating. And now you guys know how a TV works. Okay? TVs and computer monitors, these are cathode ray tubes. Okay, the next guy that we're going to talk about is Robert Millikan. He's not one of the major scientists we're going to focus on. He basically just took the findings of J.J. Thomson and he said, yay, there's an electron. Let's figure out how much mass it has. So in 1916, he came up, through the oil drop experiment, he came up with the fact that the mass of an electron is 1,840th that of a proton. So think about 1,800, think of that as a fraction. 1,840th. So if I were to take a tiny hydrogen atom and divide it up into 1,840 pieces, the mass of an electron would only be one part of that. And so it's really small. So he found the mass of an electron to be 9.11 times 10 to the negative 28, which, if I took it out of scientific notation, would have 27 zeros in front of the number. So is this a mass that we can even find on a scale? No. It's really small. Okay, so this is what we were able to determine. We've done 2 experiments. All we know about is the electron, right? Based on these small experiments, we can determine a lot about the atom. First of all, cathode ray tubes all have identical properties regardless of the element used to produce them. So it doesn't matter what element I use in my cathode ray tube, I'm going to get the same result. What does that tell you? Okay, if we were doing a cathode ray tube to determine the presence of electrons, if it doesn't matter what element I use, what does that mean? Every element has electrons, right? Secondly, they know that atoms are neutral. Well, Thomson figured out that electrons are charged. They have a negative charge, right? Well, if atoms are neutral as a whole, and we know that there are negative charges in there, what does that mean? There has to be positive things in there, too, and they're probably equal, right? Because it's neutral. The third thing he was able to kind of conclude is electrons have very little mass, so therefore atoms must contain other particles that have much more mass. So, in this part I always like to say, electrons have a negligible mass. Who knows what negligible means? Does it mean non-existent? No. Does it mean that it doesn't have mass? No. Negligible means that it is so small that when we do calculations, it will not affect our calculations. So, does it have a mass? Yes. Are we going to worry about it when we're doing math? No. Why? Because it's so small. Okay, a couple more conclusions. First of all, we have Goldstein. This was in 1886. He observed what is now called the proton. He was able to determine that particles have a positive charge and have a relative mass of 1. So in other words, it is 1,840 times that mass of an electron. Much, much, much bigger, correct? Mm-hmm. In 1932, James Chadwick confirmed the existence of a neutron, which is a particle with no charge. However, even though it had no charge, he was able to determine that it probably has a mass similar to that of a proton. So, protons and neutrons have the same mass. Electrons have small, 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 tiny, negligible mass, right? Okay, just to kind of review all the information, I just gave you a whole bunch of information, right? So, let's look at this subatomic particle chart. First of all, there's a few shorthands, right? I do not write out electrons, protons, and neutrons every time. For electrons, I do E with a negative sign because electrons are negative. For protons, I do P with a positive sign because they are positive. And for neutrons, I do a small 0 because they have no charge. Okay? And also look at the masses. Electron has a really, really, really small mass. And it's found in the electron cloud, which you guys probably remember from physical science, right? Protons have still a pretty small mass, right? But in relation to an electron, isn't it much bigger? Yes. They are also found in the nucleus. Neutrons have the same mass as a proton, again, much bigger than that of an electron, and they are also found in the nucleus. So just kind of summarize what we just found. Okay. Then, Thomson came up with his atomic model. What did Thomson do again? We're learning a lot of science today. What did Thomson do again? He found the cathode, he used the cathode ray tube to determine what existed? And they have what kind of a charge? Negative. So, Thomson's atomic model, he said, and I know that this model sounds a little silly, but he calls it his plum pudding model. He said that electrons were like plums embedded in a positively charged pudding. Thus, this was called the plum pudding model. Now remember, neutrons were not discovered until 1932. Thomson was in the late 1800s, right? So did he know about neutrons? No, he just knew about protons and electrons. So he was trying to come up with a model that fit what he knew. And so he just said that, well, there's positive and the negative, and they just kind of all float together because that made sense. Kind of, one way I like to explain it to you is kind of like eating blueberry yogurt. Some bites have blueberries in them, some don't, right? It's completely randomly mixed in there. Now, does this make the most sense? It's not very exact, is it? Scientists like to be pretty exact, don't they? So Rutherford came along and said, that doesn't quite sound right. Let's see if I can come up with an experiment to make it a little bit more exact. So in 1911, he did the gold foil experiment, which is the one on the movie yesterday I told you to watch because their graphics are going to be much better than that of mine. So what he said is, he took helium nuclei, which, if I just have the nucleus, what am I missing? Electrons. So he had a helium with no electrons. And what he did is he shot it at gold foil. Well, you guys have probably never dealt with gold foil before, but you probably have held aluminum foil. Is aluminum foil very strong? No, it's pretty weak. Gold foil is actually much, much, much weaker than that of aluminum foil. Aluminum foil is actually pretty tough. You can tear it, but if you just pull on it, it's probably going to be good. Okay, gold foil, if you can kind of just shake it and it kind of starts to fall apart. It's very brittle. Okay, so he put it in the middle, and what he did is he threw these aluminum nuclei from a source. He made them all go towards the aluminum. So for instance, if I had Leticia and Taylor stand up and hold a giant piece of tissue paper back there, and I stood up here with a cannon and cannonball and threw cannonball and fired cannons at them, what do you think would happen? They would probably duck, but if they didn't, if they stood there and held the tissue paper, what do you think the cannons would do? Go right through it, correct? Would anybody expect it to come back and bounce and hit me at the front of the room? No. Okay, but that's what happened in Rutherford's experiment. He shot nuclei at this gold foil, and if you look in the picture, all of these arrows are showing how it's deflected. This detecting screen around it was measuring where the nuclei were landing. If you look at all these arrows, did they go straight through? No. Some of them came back towards the source, and the ones that even went through were often deflected, which doesn't really make sense because you would assume cannons would go straight through tissue paper, but they didn't. So then he was like, why? Why would that not have happened? So this is how he did the experiment, though. So if we look at this, this is kind of like the results he would get. When he was looking at his detecting screen, this is what he saw. Because we can't see atoms, we definitely cannot see the nucleus. So this is how he figured out what the nucleus was made out of, what kind of shape it was. So if we look at the first picture, target number 1, we can see that we have 4 beams of light, correct? The first beam is going towards something, and it's deflecting straight up, but at a 90-degree angle, correct? So is the second one. But what do you notice about the second line versus the first line? Isn't the second line probably hitting something right here? And then the first line's probably hitting something there, correct? And then here's my second line. Okay, if we look at the third line's going and being deflecting down, and the fourth line's going and being deflected down as well. But again, it's probably, the third line's probably hitting something right there. The fourth line's probably hitting something right there, correct? But they're all happening at 90-degree angles, so it's probably going to be a straight line. So if I draw a straight line connecting these 2 points, and I draw a straight line connecting these 2 points, what kind of shape do you think is back here? A triangle. Okay, so if we look at target 2, we see the same basic thing, but what do we notice right off the bat about the lasers? They're going every which way. It's kind of, are they all going in the same angles? No. So let's follow 1. 1 is going straight through, correct? So it's not hitting anything. 2 is going, and it's probably hitting something right here, right? But we have a pretty big angle right here, correct? 3 is going, and it looks like it's hitting something right here. It's a really small angle, correct? If we go down and look at 4, it's probably hitting something right here. And we have, again, another big angle. And 5 isn't hitting anything. So the reason that there's such different angles makes me think it's probably not a straight line. So let's try to connect all the dots. If I connect these 3 dots, what kind of shape do we start to see take place? Circle. So an arch, right? But if it continued, it's probably going to be a circle, right? So let's see what it should have been. We should have saw a triangle. Is that what we saw? And we should have seen a circle. So what type of deflections do you think Rutherford is seeing? The circular ones, because we know that the nucleus is circular. So from all of this information, he was able to come up with a few facts. First of all, he said most of the particles were passed right through. Some of the particles were deflected, and some of them were actually deflected back at the source. And his actual words, which again you guys heard back in the movie yesterday, it'd be like us throwing howitzer shells at a piece of tissue paper and then bouncing back into the nest, which those shells are big bombs that we use in war. It'd be like us throwing bombs at tissue paper and then coming back and killing us and not who we're throwing them at. Okay? From this, he made three conclusions. First of all, the nucleus is small. Secondly, the nucleus is dense. And third, the nucleus is positively charged. This is why they were being deflected. It's small, dense, positively charged. That's why it was deflected in all of those ways. Okay, but remember, Rutherford was doing this to come up with a model that made sense, right? So, have we talked about his model yet? No. Okay, his model, based on his experiment, he said that the atom is mostly empty space. What does that mean? If an atom is mostly empty space, but we know it's made out of protons, neutrons, and electrons, what is that trying to tell us? Think about the distance between the nucleus and the electron. It's mostly empty space. What does that mean about that distance? Very far apart. There is a lot of empty space between the nucleus and the electrons. There's a lot of space there because they're very far apart. The second thing he said is all of the positive charge and most of the mass is concentrated in an area called the nucleus. So if the positive charge and the mass is in the nucleus, what's in the nucleus? Protons. There's our positive charge. But all the mass is there too, so what else must be there? Neutrons. The third part of his theory said the electrons are distributed around the nucleus and occupy most of the volume, which goes along with the first thing. We said there's a lot of empty space there, correct? And he called this his nuclear model. I'm going to draw you guys a nice pretty picture of what this model looks like. These were his things. These were the parts of his conclusions that he was able to determine from his experiment. I'm going to go ahead and show you what it looks like, and then I'll put this back up here so you guys can finish writing down his theory, okay? So Alright, so he said that it is mostly empty space, and in the middle we have protons and neutrons. So here we have our nucleus, right? What's in there? Protons and neutrons, correct? Okay. He also said that the nucleus is composed, or the electrons are distributed around the nucleus. So the electrons are out here in what we call the electron cloud. These are also, we can talk about our valence electrons, right? What did he say between our nucleus and our electrons? A lot of space, correct? So this was the Rutherford's model. He said protons, neutrons in the center, electrons are around But he wasn't very specific about the electrons. He just said the electrons are around the nucleus, and he would call it a day at that. Okay. So, those of you who want to finish writing those down, great. What I would like for you guys to do for the next, I don't know, if you have about 5 minutes of class left, I want you, and as long as you're doing it, I'm not going to make you write it down, but I want you and your partner to explain to each other how the Thomson did his experiment and how Rutherford did his experiment. What were the findings they found? How did they determine what the findings were, etc. As long as we're doing this activity, I won't make you write it down, okay?
How Thomson found it, or Thomson did his, and then how. What's the last one you said?